Hello, my name is Micah Flack, and today I will be covering my Chapter 3 methodology for CSC-804 Cybersecurity Research. And apologies ahead of time if my voice seems a little sore. So, just to start off with, we'll be covering the background for my research study, just to give us some context. So most signature methods rely on two types. You have the static indicators, which rely on strings, bytes, or grouped instructions within an executable. And then there's also the dynamic indicators, which relies on behavioral or patterns or things like network usage, file descriptors, file opening, sequences of commands, things like that. Could also be if certain processes are opened in quick succession. However, unless you're using a premier and closed source solution like CrowdStrike Falcon, you are probably stuck with the static and dynamic indicators like Yara for now, or Snort. Both which, those typical AV signature methods are easily bypassed, as shown in Daria Bar 2011. So the objective of this research study is to provide data on multi-arch platform binaries and invite further research and development into more rigorous and resilient attribution methods. And a little more background. So fat binaries, those are a type of executable that can be either multi-platform or multi-architecture. So that would be like with a specific cross-compiler, which we'll be discussing as part of the data collection and analysis of this research. You have LiPo, which supports ARM x86 Mach-O binaries for macOS. And you have Cosmopolitan, which supports x86 on multiple platforms, and we'll get into which specifically in a bit. And then you also have Fatpack, which is a multi-arch support for Windows. And they're not generated specifically by Fatpack, but you may have seen them before. The windows.msi files, those are also multi-arch. So some of the research questions for this study. The first one, structurally, how do the binaries differ? So again, that's going to be looking at the different fat binaries from different compilers. And then also, even against slim binaries. Then question 2, do these differences impede attribution? So think of things like packed executables. Is the fact that they're being wrapped into one executable, but supporting multiple platforms, does that impede the current attribution methods? The third question, can fat binaries still be identified using the attribution methods of slim binaries? And question 4, does the data gathered present any trends or patterns that could be used to modify the previous attribution methods? And this question should also be asking if those trends or patterns could be used to create new attribution methods. So methodology, for this research study I've chosen comparative case studies, which are described by Robert Yin, 2017, as a researcher examines multiple cases to find similarities and differences between them, with the goal being to understand how different factors may have influenced the outcomes. So typically, a case study may use qualitative data. However, with this being a quantitative study, we'll be using quantitative data, and it's not going to be a mixed use study either. And also this methodology was also chosen because from what I've read, it seems to be pretty common among researchers discussing malware, especially if it's different families of malware, but under the same type. So, like different wiper malware or different network Trojan malware. And then as for whether or not quantitative data has been thoroughly documented, VR Basili covers that using case studies and also especially comparative case studies for software engineering. That's Fier Basili, 1985. So for limitations and scope of the research study, the current limitations of analysis methods and data types. So it's going to be limited to analysis of only a few samples of memory before committing to raw storage on disk. And that's just sort of a natural limitation that you run into with this, because if you take a binary and then you blow it up into its abstract form multiple times, because there's the life data frame we'll be using, and then there's another data frame we'll be using for another library. We can only be doing so many at a time. So one will be processed, written to disk, or some database form, and then we'll clear that from memory and process the next. As for limitations with the libraries and compilers, they only support specific platforms, and architectures. For an example of generating samples, assuming we use the cross compilers, the limits for those is Fatpack, again Windows platform, supports ARM and x86. Cosmopolitan, it supports many and it's only x86. And then LiPo, which is only Mac and supports ARM and x86. So for the Python libraries, we'll be using Life, which is a executable format library. We'll be pulling like header information, section information with it. That supports only ELF, Linux, PE for Windows, and Mako. Anger, same thing, except you can also use it for analyzing memory blobs, so you don't need an entire PE. As for the compiler, Cosmopolitan, it additionally supports Linux, Mac, Windows, FreeBSD, OpenBSD, NetBSD, and BIOS, but it's all x86. So this is getting into the data collection phase. So this is an example of a ELF Linux executable format from Ange Albertini. You can also look them up on GitHub, and you can find all sorts of different formats. But what we have here is, so we have a example file, simple.r, and as you go from left to right, the detail of it expands. So of course, if you look at that executable file, you'll find the header sections, so contents executable, and then the other half. So you'll see initially the ELF header, the program header table. Those are both sections that we'll be using with Life to pull some categorical information, which will be useful for the data analysis later on, so we can group things. And then also the code, data, and section names. Those will not be used as much with Life because we'll be using more of the functional data with Anger, but it is good for recovering things like, again, the section names, and also like resource data or any possible shared data buffs. And again, just to say it again, this is mostly what we'll be looking at with the Life library. And then this is a simple example of a control flow graph, and generally you'd see this you'd probably see it with like state machine examples, but it's kind of similar, not exactly the same thing. But this control flow graph you would typically see in something like a disassembler with IDA, Ghidra, or Radar. We generate these with the Anger library, mostly because we're interested in the entry and endpoints of a function. So like block 0 at the top and block 1 at the bottom. These will help us organize some of the data we generate with Anger, called VEX intermediary representation. So that's VEX IR. But we'll be using those to generate, I guess the term would be architecture agnostic. So regardless of the architecture, the data generated is the same for whatever that functionality it's generating for. And it's generated block by block and then grouped by function, which is why we need the entry and the endpoints. So just explaining then the data generated by Anger a little better. So you have the VEX intermediary representation again, which is IR, and the control flow graphs, which the IR is generated from. So VEX IR, and the source for that PyVex 2023, has a few forms, but is the same across different architectures. So that's that architecture agnostic thing I mentioned. So regardless if you're looking at a binary from a x86 or a ARM executable, if it's performing the same functionality, it should look fairly the same in VEX IR. So the different forms you'll see is expressions, which is a calculated or a constant value, in operation, which is a modification of IR expressions, so things like arithmetic. And then you have temporary variables, which act as symbolic internal registers. You have statements, which are changes in state of a target machine, so that could be like memory read and writes. And then you also have the blocks, which is just a collection of the IR statements. So these are some specific examples of different IR expressions. So you could have a constant, so a constant value, and the VEX output for what that would look like for a constant value is 0x4i32. And then you can keep going down the list, and one of the ones that probably seems a little more simple would be the operation. So it's just a result of a specified IR operation. You can look at the output again, that's add 32, which you can probably guess is just an arithmetic operation. If you want, you can pause it here and just kind of look. Otherwise, I'm going to go to the next slide. So this is an example of what a specific ARM instruction would look like if you expand it into its VEX IR. So T0, T1, and T3, those all represent temporary registers or variables created by Anger for the VEX IR. Then you have the get, which fetches the value, and then you have 0x8, which assigns it to a register, and then the sub32, which is an operation subtracting from T0 and T1. And then you have put 16 T3, which assigns a value, and then followed up by another put 68. And then I'll just to recap, so that is the data collection for the Anger portion there, which is one of the two libraries used. And then you have here, this is just describing the basic environment. So we have public internet, the router, and then the QEMU environment host with a VLAN of 10.0.0.1/24. And then the only client on that VLAN and the QEMU server is our Remnux Linux malware analysis environment, which I can't remember if I mentioned earlier, but that has just 4 cores, 8 gigs of RAM, and a 50 gigabyte disk. So for the data analysis portion of this, so here we're just going to describe a framework, or another way you might word it is a pipeline. And it's worth reiterating, so we're not showing this because we're creating a design science artifact. This is just the analysis process in a graphical format. So we start off by ingesting our fat slim executable into our Anger CLI loader, and the CLI loader then gets processed into a Pandas data frame, and from there we generate our control flow graphs and functional data, which the functional data is just another word for the VEX IR information we'll be pulling, as well as things like function entry points, endpoints, rebased to a common base address across all samples. And then for process 3, there's a typo there. That should be LEIF executable. That's the other library we're using for extracting our executable format data. So again, think of the headers, sections, resource data, data buffs, stuff like that. And it's, again, just going to be categorical information. And from there, we have our executable format data, which both that data frame for life and the data frame for anger goes through pandas. And from there, we begin our pandas analysis stage, which there's not another slide going into that more in depth, but what we'll be doing is mapping the similarities between the pandas data frames of the life data frames as they're grouped within their categorical data. And then within those categories, we'll compare the vex IR function by function, block by block. So if we have a certain number of blocks within a given function that is similar to another function with the similar arrangement of blocks within the vex IR format, then we'll be able to say within a certain percentage, statistical percentage, that it's similar. So, and this isn't describing machine learning. It's just statistical trend data. It's just basic data science. And then from there, we will produce some charts or visualizations showing what those categorical groupings look like between the cross-compiled binaries, against the multi-platform binaries, and then also against the multi-architecture binaries. So for the validity and reliability, so to guarantee repeatability and validity of data for future research or attempts to verify analysis results, the following will be archived. So the environment VM disk, scripts used for data collection and analysis, the list of sample binaries and hashes, and then also the list of software versions used for the tools and libraries, as well as the environment itself, which I didn't mention is Ramnux based on Ubuntu 2004, Focal, and then also we'll archive any artifacts generated during the collection and analysis phases. And then also during the labeling process or the data collection phase, all MD5 hashes of the binaries will be verified using MD5sum. So we'll generate MD5 hashes of the binaries we've collected and then make sure that they match those described in the technical deep dives for that malware family to make sure that, we're pulling the right artifacts and we're comparing binaries or executables and, not like PCAPs or something. So MD5sum will be version 8.32, which is just the latest and greatest version of MD5sum. And then just to summarize again, so our objective is cross-comparison between different FAT compilers and identification of future sources for attribution of binaries. The methodology chosen was comparative case studies because it's been shown that case studies are a pretty common methodology chosen when analyzing malware. And then we're doing the comparative part because we're not just doing a single case study on one malware family, but we're doing a comparative case study across multiple FAT binary cross-compilers. And that's also multi-arc and multi-platform. So for the limitations and scope, we discussed the limitations of the cross-compilers, what platforms they support, what architectures, then also the scope of the data collection and analysis processes. Which libraries are handling what data is gathered at which phase, and then also how that data is represented and then passed on to the analysis phase and what we're looking for in that analysis phase. So that is the end to my presentation. I hope it was informative and made sense. If not, you probably have my email and can send questions. Thank you for your time. Bye-bye.